Hello everyone. So before we start today's video, I have a quick important announcement. So what I'm planning to do is I want to connect with all the people who are actually seeing through the editorials and video explanations of the problem that I solve. So what I suggest is you guys can comment your uh, Codeforces handle in the video below the video in the comment section, and what I will do is add you people as friends on Codeforces, and uh, I will also share my Codeforces handle. Those are Shadyson and Stridebreaker. Stridebreaker is my alt account. It should be visible somewhere on the screen right now. And yeah, so what I plan to do is the friend standing that after the contest, when we get the friend standing, I will give shout out to the top three people who perform in that particular contest. So that is what I plan to do. So yeah, do comment your Codeforces handle in the comment section. So moving on, let's start with today's video. So today we are going to solve few questions from uh, Epic Institute of Technology round August 2024, which was a Division 2 1 plus Division 2 contest. And so let's start. So first question is called distance coloring. Distance coloring. Okay. So in this question, you are given three integers n, comma m, and k. So what does this mean? You have a n cross m grid. You have a n cross m grid and an integer k. So what you have to do is, uh, if you are coloring any two, you have to color every cell of this grid with a color, and such that two if two cells have same color, then the then the distance between them, then the distance max of modulo of x1 minus x2 and y1 minus y2, this distance should be at distance should be at least k if two cells have the same color. If x1 comma y1 and x2 comma y2 have the same color, then the one dimensional distance between them, or what we can say, difference between the coordinates should be at least k. Okay, so how do we solve this? Suppose our k is smaller than both n and m. So we'll take an example which is given in the question. For example, 3, 3 and 2, where n is 3, m is 3, and k is 2. So 3 cross, we'll have a 3 cross 3 grid. And how do we go about coloring the grid? So definitely we can color the first grid as 1, and the cell next to 1 will cannot be colored with 1, will color it 2. Now the thing is, the next number can only be colored with 1, because can be colored with 1, so we'll use it. Now we come back to this grid. So now we come back to this. Now this cannot be colored 1, this cannot be colored 2, so this must be colored 3, and this must be colored 4. But now if you look at this thing, it can be colored 3, and similarly we can color this 1, 2, and 1. So what essentially are we doing? So we are essentially getting k into k many colors to color this grid. So if this grid was even larger, say 4 cross 4, so we can have 1 2 3 4 in this fashion, 1 2 3 4 in this fashion, 1 2 3 4 in this fashion, and in this 1 2 3 4 in this fashion. So when k is both less than n and m, when k is less than both n and m, the answer is k square. But what if k is greater than n and m? So in this case, if k is greater than n and m, greater than or equal to n and m, the best we can do is since every coordinate will be every number will be closer, every cell will be closer to every other cell, so we'll have to color all the cell differently. In this case the answer will be n cross m. So the only case that remains is when if suppose without loss of generality, if n is greater than m, then what if m is less than k is less than m, or something if something like this occurs, if k is between n and m. So what will we do in this case? In this case the answer will be k into m. If m is smaller than n, in this case the answer will be k into m, because for example if you take the case which was given 254, so we will have a grid like this. So we can color these people as 1 2 3 4, and the next person can be colored again as 1, and then we can go from here 5 6 7 8, and this person has 9. So 4, the answer would be this won't be 9, this would be 2, this will be 5, sorry. But yeah, the thing is the answer is 2 and the answer is k into minimum of n and m, because this is how we plan to color the grid. So essentially the based on the case the answer is so if k is greater than n comma m, the answer is n into m. If k is less than n and m, the answer is k square. And if k is between n and m, if k is between n and m, the answer is k into minimum of n or m. So this was the first question. Moving on to the second question. So second question was a removals game. Okay, so in this question we are given two permutations two permutation A and B. So A and B, so this belongs to Alice and this belongs to Bob, and this is a two-player game. And in this what happens, the permutation that Alice has, what she can do, she can take the either the first digit or the first not the first digit, first number or the last number in the permutation and remove it. And Bob can also do the same, take either the first number or last number and remove it. And if at the end, if in the end the number of the number that remains, if after so this game will be played for n minus 1 turns, and if first digit and if the number that is left with Alice is equal to the number that is left with Bob, then Bob wins. If Alice has if a number of Alice is different to the number which Bob has, then Alice wins. So if both player plays optimally, you have to find who is going to be the winner. Okay, so let's try to solve this question. So what if Alice and Bob are given the same permutations? So for example 1 2 3 4 6 5, and Bob is also given 1 2 3 4 6 5. So Bob can always win in this situation by selecting the same playing the same move that Alice plays. If Alice plays in the beginning, Bob will also play in the beginning. If Alice plays at the end, then Bob will also play at the end. So essentially, whatever Alice does, Bob will do, and Alice will win. Okay, but what if these permutations are not equal? So for example, 1 2 3 and 3 1 2. Alice has this and Bob has this. So in this case, Alice has either the chance to play 1 or 3. But in this case, Alice can play 1 because since 1 is for Bob, the number 1 is at the center. Since 1 is at the center, Bob cannot delete the 1. So so Bob has to delete something other than 1. So if Alice deletes 1, then Bob will have to delete either 2 or 3. No matter whatever Bob delete, so suppose Bob deletes 2, then Alice can play in a way that such that she preserves 2. I will take a bigger example. So for example, Alice has this permutation and Bob has permutation 1 5 2 3 4 6. Okay. Now if you look at this, if Alice plays 6, Bob won't be able to play 6, So Bob can either play 1 or 5. Bob can either play 1 or 5. So if Bob can either play 1 or 5. Okay. So if Bob plays 1, then Alice can play in the other upcoming round. She can play 5 4 3 2 and preserve 1, such that and if she preserves 1, definitely Bob has already deleted 1, so Alice will win. So this is the case. And there's also another case where Bob can win if, so what we want is so for Bob to win, Bob should have an array in a way that after deleting a particular element, it should have the same access to the same element that Alice has. So this is also possible when the array B is reverse of array A. So for example, if array A is 1 2 3 4 5 and Bob's array is 5 4 3 2 1, if Alice is delete 1, Bob can delete 1, and Alice got access to number 2, and Bob also got access to number 2. This is only possible when A equals to B, or A is equal to reverse of B. So that's the case. So all you need to check in this question whether A is equal to B or A is equal to reverse of B. If these are the cases, then Bob will win, else Alice will win. So yeah, this was the Removes game second question. Moving on to the third question, black circles. This was an interesting question. Okay, so in this question, we are given n centers and n centers of circles. Initially, the radius is 0. Initially, radius is 0, and we are given a start point. We are given an end point, and we have to reach from start point to end point. We have to reach from start point to end point, but there's a catch. You can only move one unit in any direction that you want, and thus the n circles are these n circles are growing their radius at the rate of 1 unit per second. Okay, so so we have to determine whether you can reach from start to end such that you never encounter this enlarging circle anywhere in your path. You have to check whether that is possible. Okay, so now this question took me a while until I went and saw the example test case, the explanation to the example test case in the below. So the solution to the problem is, so from you, if you can move in any direction however you want, so look at the start point and look at the end point. So the shortest distance between them is the straight line from start to end, and that will be the shortest amount of time that we will take to reach from start to end. Okay, now the question is clearly, if any other circle center lies closer to the end than how we are from the start distance from the end. If any circle lies closer, it is clear that this circle's radius will reach the end faster than us. So if that's the case, we can directly print no. But what if something like this happened, that uh, on our path, if what if something like this happened, that on our path we end up touching a circle like this somewhere on our path. But if you look at this clearly, so what essentially might happen, that you are going from start to end, and somewhere in between you hit one of the circles. What if this happens? But I can guarantee this will not happen if all the points are away from the if all the points are even further away from the end than the start is. So suppose this is start, this is end, this is the path you are supposed to follow, and suppose any circle, suppose there is a circle that touches you before you reach this. Okay, so before you reach this point, there is a circle who grows and touches your path before you reach it. So in that case, so in this case, the distance from start to end, if you look at distance from start to end, so suppose this distance, if you look at distance from start to end, and from this circle to end, this distance will okay, sorry. So if this distance will be lesser, this distance will be less than distance between start and end. So this distance will be less than start and end. So in that case, but we already concluded that if the distance from start, if any circle has its center's distance less from start to end, then it's a no go. So all you need to check is basically whether the distance between start and end is less than a distance between less, whether the distance between start and end is strictly less than distance between end and all the centers. That's all you need to check. Okay. Moving on to the fourth question, D1, that is DFS checker. Actually, I wasn't able to solve this question. I wasn't able to solve this question during the contest, but I made a small mistake, which due to which I couldn't. My question was getting wrong answers, but yeah. So in this question, this is the easy version of the question. In this question, we are given a complete binary tree. Specifically, and so a complete binary tree has 2 raised to n minus 1 many vertices, and the depth is n. So if n is equal to 3, then we have 2 raised to, not minus 1 won't come here, minus 1 will come here. So we have 2 raised to 3 minus 1 is equal to 7 vertices. So we'll have like 1 2 3 4 5 6 7. So this is the tree that we will get. Exactly this tree will get. Okay. So we are given a tree, we are given a permutation, and we are given a permutation. This permutation essentially tells us ki this is one of the possible DFS traversal of the tree. So what is the DFS traversal of a tree? For example, if for the tree that we made, in this tree, the one of the possible DFS traversals is 1 2 5 4 3 7 6. So this is a permutation, but this is also valid DFS traversal, because after 1 you can go to 2, and then from 2 you can go to 5, then again we'll go back to 2, but 2 is visited, so we'll go to other children of 2, that is 4, then we'll go to 3, then we go to 7 and go to 6. This is a valid DFS traversal for the question. So this permutation P denotes DFS traversal, and we are given q queries of the form x and y, and we have to answer that if in permutation P, if px and py are swapped. If px and py are swapped, is it a valid if px and py are swapped, we have to check whether it is a valid DFS traversal of the given tree or not. Okay, so how do we go about it? So let us take the example that is given in the question. When n is equal to 7, in this case the tree will look just like how we drew earlier, and we are given the permutation. Initially the permutation is 1 2 3 4 5 6 7. Okay, now since this is a complete binary tree, what can we infer from this permutation? We know that the one will be the, from this permutation we can definitely find out that 1 will be at the top. Who are the children of 1? Definitely 2 will be one of the children. Then the number 2 will be one of its children. 3 will be the children of 2. Now it can happen that 4 is the child of 3, or 4 is the child of 2. How do we determine this? Because now we can find out based on we'll find that out based on the depth of the particular numbers. So what is depth? I will come to this, but if we construct this tree, then 4 should come here, then 5 will be the other child, 5 will be the other child of 1, and the two children of 5 will be 6 and 7. Now the question is, how did we determine who are the children of 1? So before we find this out, let us give the notion of depth to each of the vertices. Okay, now since 1 is the root, now let us 1 is the root, then uh, the root will have a depth, will give the notion of depth, will give it depth 3. I shouldn't say depth in this case, I will call it height or something. Then the layer below it will have depth 2, and the layer even below it will give them depth 1. Okay, how do we calculate this quantity? We basically have n, n is equal to 7, we'll add 1 and take a log of it. We'll add 1 and we'll take log base to the power 2 is essentially the number of time we can divide it by 2. Okay, so the root will have depth 3, the layer below it will call it depth 2, the layer even below it will call it depth 1. Okay, so now if your depth is equal to 1, so if at any point if your depth is equal to 1, you won't have any children. But if your depth is greater than something greater number, so who will be your children? So in this case, one's children will be 2, so the depth of 1 is 3, one's children will be 2, and it will, if this is one of the child, then it will have a lower depth, and the other child of 1 will be, if depth so child of I will be, if depth of I is unequal to 1, if depth of I is not equal to 1, then the child of I will be I plus 1 and I plus 2 raised to depth of I minus 1. So essentially the other child of 1 will be 5, and that can be found out as 1 plus 2 raised to depth of I is 3, minus 1 is 2, and 2 raised to 2 is 4, that will be give 5. So the another child of 1 will be 5, and it will have depth 2. Then the children of 2 will be 1, because I plus 1, and the other depth will be this. And the numbers with depth 1 don't have any children, so we'll move further and we'll have this. So from this we can find out who will be from this we can determine the tree that we'll get from the permutation. So essentially, if we are given a permutation which was in this case 1 2 3 4 5 6 7, we essentially find out ki what is the depth of them, depth of the people. We found their depth, and from this we can also find, according to the permutation, who are which index their parents lies. So in this case so one does not have any parent, so we'll call it minus 1. The parent of 2 lies on index 1, the parent of 5 lies on index 1, the parent of 3 lies on index, sorry, this should be 0 0. The parent of 2 lies on index 0, the parent of 5 lies on index 0, the parent of 3 lies on index 1, and 4 also lies on 1, the parent of 6 lies on index 4 and 4. And we how to calculate this quantity? So basically, when we calculate the depth, when we find this depth wala array, at the same time we can calculate the parents of permutation in this. Now along with this, we'll maintain two other variables, that is has valid parents and count of invalid locations. So what are we essentially doing with this? So if you look at this, if you look at our original tree, if you look at this original tree, now if you look at 7, we'll write 7 as 1 1 1, we'll write as 3, 3 as 1 1, we'll write 6 as 1 1 0, and 3. If you see the the parent of any number is the right shift, if one right shift of the number itself. So if we right shift 6 by 1, we'll get 1 1, which will be its parent, which will be its valid parent. So what we can do is, from the permutation, so we'll maintain this has valid parent array. I'll just call it hvp as has valid parent. And you look at this permutation. So for index 0, it will call it has valid parent if that number is equal to 1. So this one has valid parent. Now look at 2. 2's parent is at index 0, and whatever that number is, you can get by right shifting 2 by 1 unit to the right. So this also has valid parent. Look at 3. 3's parent is 2. So 3 can be written as 1 1. 2 is written as 1 0. If I right shift 3 by 1 digit, we'll get 1. But 1 is not equal to 2. So 3 does not have a valid parent. So we'll cross this out. Okay. Now look at 4. 4's parent is 2. 4's parent is 2 because it lies at index 1, and we have 2 at index 1. And if we right shift 4 by 1, we'll get 1 0, and that is equal to 2. So 4 has a valid parent. Look at 5. 5 shouldn't have 1 as the parent, so this will be false. 6 has a valid parent and 7 has a valid parent. So, and when we take the count value, that is equal to 2, that we have two indices where the parents are invalid. Okay. Now we are processing so we maintain these two things. Now we are processing the queries of the form x comma y. Now if we exchange x comma y, so if we exchange x comma y, what would happen? So in a tree, if we exchange x comma y, then each x will have one. So which all indices in this will, which all relations in this array will get affected. So if there lies x somewhere, okay, suppose this was your x and this was your y. If we exchange this two, the entire trees remain same except these values 1 2 3 and 1 2 3. Excuse me, so sorry for that. So these three relations are, at max 6 relations are changed. So what you have to do is, after exchanging x and y, we just have to check whether these three are placed at their valid positions, and whether they are going to their valid whether these people are having their valid parents or not. Based on that, what we can do is, we can update this hvp array has valid parent array, and increase the count based on how many are fixed and how many are not fixed. So because at max only 6 are getting hampered at a point. And when we do this, we update this count value, and if count is equal to 0, which means the array, the permutation that we have is a valid permutation, so we'll print yes, else we'll print no. I'll run through a quick example of this. So in the first query, we are given first query of the second test case, we are given 3 comma 5. So if we exchange 3 comma 5 over here, if we exchange, so initially the tree look like 1 2 3 4 5 6 7 like this. If we exchange 3 and 5, so the new tree will look like this. 5 4 6 7. The new tree will look like this, but now the only places that are affected are this. Okay. Okay, in this case, sorry, I made a mistake earlier. So even these two are no, even these two guys don't have their valid parents. My bad. So yeah. So now we'll have to check whether all these places are all these places are satisfying. Actually, we don't have to check all these. We just have to check whether this is valid, and this four places we have to check whether they are valid. So uh, after the exchange, this three places are the ones we need to check. Okay, so now whether we have to check whether phi is valid parent is true. Yeah, that is true. And initially this position was false, but now it becomes true. So this position was false, now it becomes true. So so initially the count was 4. Due to this it will become 3. Now this position is entered. Now look at 1 comma 3. So parent of 3, valid parent of 3 is 1. So even this gets handled. So this becomes correct and the count drops to 2. Moving on, the parents of valid parents of 6 and 7 are supposed to be is supposed to be 3, and that is also a valid change. So we'll increase this, will make even this guy is true, and the value will become 0. The count will become 0, and it should return as yes. So yeah, that's how you get this question done. Yeah, so that's it for today. Thank you.